OK，好，那我们等一下就开始。So this week, we'll continue to talk about diffusion models, mostly about fine-tuning and some advance in some more modern models like Stable Diffusion 3. There are also even more modern models like Flux, Hydrogen, or even newer models. But in this week, we'll talk about the advanced up to Stable Diffusion 3 later on. And we will have our homework, which is including to do the fine-tuning. For this homework, we're asking you to do Dream Boost training. 好，所以这个作业主要做的是一种 fine-tuning。那 fine-tuning 有很多种，那这个是用一个比较以前一点点的，但是其实原理都差不多。OK， so Dream Boost you may rarely hear it recently because this is old terminology, but it is including one type of fine-tuning for a diffusion model. Especially, it is very popular for like stable diffusion model fine-tuning. So you can follow these instructions to do the fine-tuning. So for a general fine-tuning process, we are using here this note to conclude, to summarize a few popular fine-tuning methods. 好，所以我们一开始会先介绍一些怎么去微调diffusion model 的方式啊，会在这个 note 里头。So, but before we introduce the fine-tuning, let's first recall the architecture of stable diffusion. So it is quite important that you familiar with the architecture of a stable diffusion. The architecture is in fact quite like the architecture of latent diffusion. So it will have a encoder and a decoder, a variational autoencoder, to encode the image into or decode the latent back to the pixel space, or like encoding the pixel space image into latent space. 好，所以它第一个元件就是 VAE， 它可以做 pixel space 跟 latent space 之间转换。Then it has a unit which is doing the primary job for diffusion process, denoising process. This is usually called a unit, or like in a modern model, it's used like a DIT, diffusion image transformer, something like that. But if you see something like a unit in the context of diffusion models, usually it refers to the denoising part of the model. And we were mostly using a attention unit right here in stable diffusion. Also, it has some conditioning that encoding like text, mostly for a text prompt, and injecting the prompt into the training process. This unit takes some parameters. One of them is a noise image, and it also has a step information, which step it is. And finally, it got some conditional information. So it usually has 3 inputs and only 1 output. The output is used to predict the noise that has been added to the image. 好，所以基本上就是这2个元件嘛，一个是 VAE， 一个是那个 unit， 然后再来就是用一些方式，通常是 clip 去把文字做一些 condition， 然后 unit 通常会有3个 input。你其实看这东西最主要的就是看它的 input 和 output。那它有3个 input， 一个当然就是加杂讯的图片，因为它最后要 denoise 嘛。然后再来就是另外一个是那个 你是哪一个 step 因为它本身要跑很多 step，所以这边的话你要知道它是哪一个 step。最后当然就是那个 condition 通常都是文字的，目前来说都是文字的 condition。你就是吃这3个东西，然后吐出来的是杂讯就是本来那个你要预测那个图片以后加了哪些杂讯进去，所以你 output 的就是杂讯。所以如果你看得出来这几个部分，那个程式码你就会比较容易能够看得懂。Okay, so just recall that we have this latent diffusion architecture. Stable diffusion is mostly has exactly the same architecture except the condition part. The condition part is mostly using the classify-free guidance. Other than that, it is pretty much similar. But for the classify-free guidance, the difference between classify-free guidance and classify guidance is mostly in the training, in the laws, in the training process. The training process is different. Other than that, they are pretty much similar. I mean, in practice, the unit always take the condition, the encoded text, or other condition as input. So they are pretty much the same. Okay, so let's see some popular or famous fine-tuning method. So there are a few of different fine-tuning methods that you can find in the Hugging Face diffuser notebook. Here is a pretty good source that you can study in detail of how diffusion models works in various different forms. So here is a collection of notebooks from Hugging Face diffusers, including like if you want to understand what is the clip guided method, here is a clip guided stable diffusion with diffusers, and also there are instruction pixel to pixel. Here there are a few of the different Dream Boost LoRa examples that you can find for as a reference. We are using another one, but you can actually look into these notebooks, and if you want to learn more about the Dream Boost and the LoRa fine-tuning. Also, here is Instant ID. We are not talking about discuss Instant ID, but Instant ID is also a very popular method. And also ControlNet, where we will discuss it in this lecture. There are also flags with classify-free guidance. CFG usually refers to the classify-free guidance method in the diffusion model context. And also, if you are interested in how does the image-to-image works, here is one example for using diffusers. There are many different ways to do the image-to-image generation. Here's a few ways that you can do. And also, there are many different ways to do implanting. Here's a notebook that illustrates some of the basic, I would not say naive ideas, but I mean, if you really think about it, there are a few apparent ways to do image implanting or image-to-image generation. And even before you actually doing it or doing the experiment, you probably can imagine there are some ways that you can do to use diffusion models. Although the diffusion model itself is generate image from a total noise, a pure noise, but you probably can imagine a few ways that you can do to do the image-to-image translation. For example, maybe you don't, if you got an image, maybe you just add some noise to it, like 20% of noise or 30% of noise to it, and then denoise it and guide it by some prompt. That might work as an image-to-image generation. 所以比如说一个很 naive 的方式，就是因为 diffusion model 本来是从那个全部的 noise 直接生图嘛，那有没有什么可以图生图的方法？就是在没有人告诉你的情况之下，你大概可以猜出1-2种 常见的方式，比方说我一张图可能就加个20%的 noise， 我不要加到100%，让它变成全部 noise， 我就加20%的 noise。加了 noise 之后呢，我就 denoise 嘛。那我 denoise 的过程，我可以用文字去引导它，那这样不就是变成一种图生图的一种方式了吗？那 impending for impending is we can actually do similar things like okay, we add noise to certain region that we want to do the impending, maybe more noise on it. And when we do the denoise, there are multiple of kind of apparent choice. One way to do that is we reverse the noising process because we already know how we actually add a noise into an image because we already got the original image, right? And we are literally adding the image to make it on the image itself. So maybe we can just reverse the actual noise process on the regions that is going to be impacted. And we doing the actually, using a model to do the denoising on the impending, the region that we wish to do the impending. So maybe that is one way to do the impending. 好，所以做 impending 的话 ，impending 就是把一个区域，比如说你要把椅子上的一只狗移除掉，或者是把它换成一只猫。好，那个区域我们希望能够换掉东西，但其他区域我们希望保留。好，那有没有什么一个你虽然我们拿到只有前面的 diffusion model 嘛，但是有一些很明显的方式你可以做 impending 啊，比方说你就加杂讯嘛 ，diffusion 不是加杂讯然后去杂讯嘛，然后你就加杂讯，然后其他的部分你可以照正常的 denoise 的部分把它反过来，因为你本来就是一步一步加啊，比如说你说加了1000步好了，每1000步你就慢慢加杂讯，你就照原本的方式慢慢把它倒回来，因为原来是你加的嘛，你就可以把它照正常的方式倒回来。只有在那个要做 impending 的那个区域，你用你的模型去做 denoise， 哦，这看起来也是似乎是可行的。那当然也可以用其他的方法嘛，就整个区域你就加20%，然后就像刚才一样加20%，然后 denoise， 然后或者是说，你的 region 里头，就是你要 impending 的，你就多加一些杂讯，在其他 region 不要加那么多杂讯。那这样看看会不会有什么效果也可以。But so you probably would have some naive or like fundamental basic idea of how to do impending, to do image to image translation, or do other things, maybe like doing the video encoding. There are plenty of naive or apparent way to do so. So the first step is that you always have to think those options before you actually read a paper or like reading this kind of things. Otherwise, some of part is actually trivial or like pretty much very straightforward. If those kind of things you still need to learn from literal or like to reading something to learn that thing, that will make things much harder to actually understand the important or the most valuable part of the paper, because there are certain experience that or like the experimental results or the thought or like findings that cannot be get or like find by purely imagination or by your like logic reasoning. There are something that you cannot infer. You need to do some experiment. Those parts are very important and valuable, and there are information in those paper. 所以在一些就是刚才那些基本的那些想法那些东西，你一定要先能够自己产生啊，不然的话，你会读 paper 的时候会读得太用力，然后你会抓不到重点，因为刚才那些东西是你可以自己想到的。你要是自己想到的东西都还要被读出来的话，你会忽略掉真正需要被读到的东西，因为它有一些实验的一些重点啊，还有一些细节。哦，这程式码也是一样，它有一些细节，那些细节是你一开始没有想到的，是想不到的东西，那些东西才是它真正重要。还有一些实验的结果，还有它的一些想法。 那些东西是你一开始照常理去推断的时候会想不到的东西。那些东西才是你读这些东西重要的部分。Okay, so let's go back to the fine-tuning part. Let me get it here. Here, yeah, the fine-tuning part. There are several ways that we can do fine-tuning. Okay, so the first part is that we just visit a bunch of notebooks that contain a lot of things. I strongly suggest you to like browsing the notebooks that seems to be interesting to you. Then you can actually run them on a collab or maybe on your local machine. Because the notebooks has been already created and the people were trying to run them. So they are pretty easy to run. So even though you probably don't have enough energy or like time to dig into it, still just run and see what it happens. That and has an idea of that, okay, this notebook existed. So once you will need it or like thinking about something that require the knowledge that may be provided in the notebook, then you can go back to a notebook and go deep into it, dive deep into it and study the details. Also, I strongly suggest just look around and see how this notebook works and trying to understand what they are trying to explain or the treasure behind they are trying to provide it. Okay, so here are a few of the fundamental methods that we can use to actually doing the fine-tuning things to make the diffusion model more, to customize the diffusion model to our need. So the first method is textual inversion. So it is also one of the easiest way or like naive or apparent way to do the fine-tuning, and it is like a lightweight fine-tuning. So how does it work? The textual inversion basically add some new token or like new word into the text encoder. So we are using clip in like stable diffusion. Sometimes we are using T5 in more modern models, which we probably will discuss later in this lecture. But for like stable diffusion 1.5, 1.4, or 1.3, it is popular to use clip as text encoder. So like other large language models, these text prompts are first encoded into tokens. So there is a tokenizer to encode them into tokens. And they pass through some kind of model, transformer models. It has some attention block or like transformer things. And finally, they encoded things into latent. Okay, so but the thing is, like, for example, if we wish to make describe the image, like we are telling in this example, like for example, we wish to generate images in like the JoJo adventure, the adventure of JoJo, a bizarre adventure of JoJo style images. So if without fine tuning, we probably will have to discuss what this style is, like maybe 80 or 90 more colorful Japanese animation style in a more exaggerated posture or things like that. But you cannot describe it in a, it's kind of difficult to describe it exactly. 好，所以首先第一个就是它的构想就是好，我们可以比如说好了，我们希望它能够生出像是JoJo 冒险野狼这种东西的那个风格好了。那你想象的就是我在 text prompt 的时候，我就尽量描述它就是比较夸张的一些姿势，然后颜色对比度高啊，日本的可能90年代动画风格之类的。 但是你很难那个很精确的描述。So because it kind of possible to describe the things in the text prompt by using a text prompt. It is possible, but it's kind of difficult. Potentially it is possible, but maybe it's too difficult because we're not entirely sure that what is the effective working length of the limit of the text prompt. Maybe there, if you have 1,000 tokens, maybe it's too long because the diffusion model is not trained in that way. So maybe if you have maybe there is a effective length limitation for a prompt. So that limit your possibility to actually describe these styles in text. So potentially it is possible, but it may be difficult. So how about we change the text encoder a little bit so that, okay, maybe we add some words like JoJo style. We'll make a JoJo style a token, this word a token. Or maybe we just invented something like XYZ because we can invent any word. So we invented one token called like XYZ or X123. We make it a new token into the system. And we train because every token has an embedding. So recall that in a language model, first we tokenize, and every token we have an embedding matrix, right? And we can do the embedding to find the embedding of this token. So maybe we can find a spatial token. I mean, first we construct a new token. Let's just call it a JoJo style, a token, a spatial token for JoJo style. Because we can manipulate a tokenizer is just an algorithm. We can manipulate it pretty easy. Okay, so we add a new token. The only thing left is to let the model knows what is the embedding of this new token. So we can training the model by adjusting the embedding of this token so that it can generate the style of the desired style. In this particular case, in the JoJo Adventure style. Okay, so that's the idea. So can we actually do it? So how even before we're going to see the actually notebook, we can imagine how we do it. We probably should mimic the original training process of like a stable diffusion, like the same laws, same same training loop, so which we will see inside it. And we probably should like freeze everything else, like the unit or maybe the VAE, the variation autoencoder. We are not going to train them. We only need to train one thing, that is the textual encoder, which is the clip part. And we probably should fix everything else. We should, because there are a lot of different embedding and there are other weight in the textual encoder. We probably should also freeze them. The only thing we need to train is the embedding of the new token. So we probably will expand the embedding matrix a little bit. Just add one more component and add a new token to the system so that the tokenizer can recognize the new token. So that's the idea. Before that, let's see some a notebook that is okay. It is still there. It just does not. You probably can still download the file and show it by yourself, but unfortunately, it is not. Let me check. Okay. You probably cannot see it yet. Let me share the notebook. Okay, here is the notebook that shows in my Visual Studio Code. So the idea is to learning this teapot, this teapot as a new word, and it has already been trained. And this one is this kind of style. So this notebook shows the result of the things. You can use this notebook to check the result of the fine-tuned model by using texture inversion. So it invented a new word. You can see that here, the new word is a cat toy. It's kind of small. Let me try to increase it. Okay, you can see that. Here, it invented a new word, a new token called the cat toy. The cat toy. Okay. So after it load it from the it called the conceptual ID, kind of like a repository of the fine-tuned model. You can still use it. It is it is existed in the Hugging Face repository, so you can get it. So and you can publish your own, kind of like GitHub, but on Hugging Face. So here it invented a new thing called the cat toy, and you can see that it generates like a gravity of this cat toy. It has been already trained. Okay, so this is one example for the inference. Let's go back to the other notebook. Hopefully it is not working, but I can download it. It is just not rendering in like a GitHub, but the notebook itself is there. It's still there. Okay, so let me share the Visual Studio Code. Okay, so this is a notebook for the training. It can be used on like different hardware, like Colab. It's specifically designed that can work on Colab. So you can actually run this notebook on a Colab. So it detects different hardware using a different like X-former. But these are all just detail things. You don't actually need to log into Hugging Face Hub if you are not trying to upload your resulting models. But still, some model requires login to download. If you are setting your Colab correctly, it should be no issue at all. But I believe that older models like Self Diffusion 1.3, 4, or things 5, maybe 1.5, probably does not need this login at all. Okay, so here are just some utility and some images that you can use to do the training. Okay, so it download all those images for training. Everything is on a cat toy, a folder called cat toy, like this one. So here is the training image. You only need like 520 image. You don't need to collect like 1000 because this is just a very lightly training. You only need to collect a few image. The training process is quite fast. So here are a few different ways to do the training. Like, okay, do we want to train a new concept like an object? Or because eventually we are trying to create a new token. This token may be referred to an object or referred to a style. But all of the differences You may say, okay, what is the difference between object and style? I know what is the difference between them. An object is an object like a toy, cat toy, like here. A style is like what do I do for like a JoJo style. I know that, but what is different? What is there different in practice? Like when we do a training, how should we handle them differently? The thing is, the only difference is that in the prompt, for an object, you refer this object like an object, like this is a cat toy on the table. This is a cat toy on the desk or on drawing on the wall. But if this is a style, you say that we are painting something in like a cat toy style or like a JoJo style. So the only difference is the prompt. And also, we can initialize, like we say, the only thing that we need to train is the embedding of this new token. Or in this case, the new token is the cat toy, the whole thing. This whole thing, you don't need these symbols, the triangle, the symbols. You don't need this the greater than or less than symbols. You don't actually need them, but with them, it is easier to identify a new token. Maybe avoid the possibility of, because the tokenizer is a pretty complicated algorithm. So with these spatial symbols, it will probably more ensure that this guy is going to be like a whole token. Okay, but anyway, you can use any. In principle, you can use any string to be a new token. But this new token is better to be something to be unique, so that it's not confused with other word. So, for example, if you doing things like cat toy, like this one, you can still do things like this cat toy. But because I believe that cat itself or toy itself is already a token, so it may confuse the tokenizer. So it would be better if you use something unique, or you maybe use like X, Y, Z, 1, 2, 3. That is also okay. It just in these styles, it balance the readability and maybe uniqueness. So it is their choice. So they are not potentially you can use anything, but they are not all equal. But I think uniqueness is above all other things. But yeah, if you really like things like this one, you can probably also do that. But I don't know why you. There's no reason to insist on it. So okay, anyway, just use some unique things as your token. But what I was trying to say emphasize is that we need an initialized token. The reason is that we can initialize this new token, the embedding of this new token to be anything like a randomized. You can initialize them random, but it would be better if you get a better starting point of these things. So one way to do that is we are trying to use a existing token, maybe a cat or maybe a toy, as its initial value. So these things means that we are going to use this initializer token. So this one need to be a token. So if the toy, suppose that a toy is somehow it is not a token, it will report some errors so that it cannot find the token, cannot initialize it. But the idea is that we initialize with something probably already similar to our idea. So in a case like the JoJo animation style, we probably start with something like animation or like anime, ANIME, or like cartoon, or maybe like manga or something like similar to it. So in this case, it initialized with the token, the embedding of the toy. Okay, so when we do a training, we need a bunch of like text prompt. So in general, we use a template. You can modify them, but for each image, we are using some more very generic text prompt, like a photo of a cat, like in this case, a cat toy, a rendering of a cat toy. Usually, you like if you have five sentence is probably already okay, but here it has like maybe like 20 sentences. It is never will never be too many. You can use like 100 if you can do that, but I think if you have 5 different sentences, it would be probably sufficient. Okay, and it will generalize. I mean, if you use like training it with like the first 5 sentences, probably if you are doing the inference using like a rendition of a cat toy, it mostly likely it will work just fine. So for example, like in the inference notebook we just saw before, it actually use a graffiti on a wall, right? We didn't see a graffiti right here. There's no graffiti sense right here, but it works as well. So you probably only need like 5. You are not trying to train it too long, and because most of the part are frozen, so you don't actually need too many different sentences. It will generalize quite well. Um, but because it is a very simple training, the result may not be as good as a modern method. But this one is very easy training and very lightweight, very very simple. So it cannot be go too wrong. There's nothing go wrong there. Everything is frozen except one latent, one embedding. Okay, so if you want to try to do some customization, you can still start from textual inversion as your baseline. Okay, so if we are using style, currently we are using object way to the new token is an object, is not style. But if you are trying to use a style, here are the problem. This is the only differences of this like object training or like a style training. So you can see that a painting in the style of something. So the idea is that it's pretty common sense, right? If you have a style, we just train it with a bunch of different things called a photo in the style, a painting in the style of something. That's it. So if you 就是你可以举一反三嘛，就是如果你要同时训练 ，so if you want to train like 2 tokens, one is an object, one is like a style, or maybe you have like 3 style with 3 object. You want to mix and match of them. That's easy. You just use a painting of in the style of something, a painting of like a cat toy in the style of JoJo animation. That's it. You can just free to do that. There's no limitation of like object or like style. There's no like a period limitation on it. It's just a common sense. When we do want to do the style, we describe it as a style. When it is an object, we describe it as object. There's no rules or like regulation on this sense. You just do it freely. 好，所以这边其实就有点像我之前讲，就是你做这种东西的时候，这个东西你一定要先自己有个概念。如果碰到那些问题，你先心里想要怎么解决，因为有的时候，如果你是这边是用读的，就是说你一开始就说我就是抱着我就是来学习的心态，我什么都不想，我就开始读，你会觉得说这个东西就是一个是物件，一个是一个 object 嘛，一个是 style。那我如果要混合在一起，那这变成一个完全新的东西，其实也没有，这边就是尝试而已。这一块就是没有什么就是尝试嘛。 我总是要一些 prompt， 那我 prompt 要怎么写？就尝试了。那当然，有些人不是尝试啊，比如说我前面告诉你的经验就是，你这边其实五句话就够了。那这边可能就，不过那也算是一个常理啦，只是说它比较偏向训练上的常理。可是像这种，比如说我这句子为什么要这样写，或者是为什么分成 style 或 object，很单纯的就是，如果你是 style，你不能说 a photo of a nice 什么 JoJo animation。如果它是一个物件，你不能说 a painting in the style of a cat toy，你不能这样说嘛。所以它把它分两个。那如果你是要混合，比如说三种物件、三个 object、三种 style，而且你知道哪一张图是哪一个物件跟哪个 style，那你就做对应的 prompt 啊。所以这完全就是尝试而已。哦，So a lot of thing is just common sense. There's nothing. I can explain it in a very detail, but I don't think that is necessary because um I'm pretty sure you can understand or realize every the reasoning or logic behind by simply using common sense. To explain a common sense is very difficult. But the thing is, you need to start it to actually think about it in a more common sense way. Okay, so this is a prompt part. The actual part that is not common sense is the following, more like a technical details. But they are also kind of common sense in not the common sense, but they are common sense in programming. Okay. So first of all, we need a data set. This data set is Hugging Face data set. I believe we can go to. There's no definition. Okay, I haven't set it in a full setting, but usually, and this is in a notebook format. Notebook format is kind of difficult, but usually I can actually go to check the data set, the definition of data set, but I cannot find it. Maybe go up one. Okay, here. Okay, it use a torch dataset, not the Hugging Face dataset. It use a torch dataset. Okay, it is using a torch dataset. So it actually inherent the like subclassing. In Python we call subclassing the dataset. This is a common practice in torch dataset things. But basically, the thing is that we are trying to get this item. We are trying to return a prompt and the image altogether. A prompt may be just randomly chosen from a template, and we encode the image like in usual, like kind of normalize it into the value between -1 and 1, and we return this example randomly. So this is a common practice to actually customize our dataset. Okay, and we load the tokenizer. This one is a Hugging Face diffuser things. First of all, they are kind of like a transformer, Hugging Face transformer. It has a pipeline things. So if you are trying to use the model, most of the time you just use a pipeline. But also there's APIs that you can load each component separately. So in this case, because we are trying to train the things, so we are loading everything like tokenizer separately. And we add a new tokenize, new tokens. So here we add a new tokens right here. So in principle, you can actually improvise a little bit. If you have more than one token, you can do similar things. Okay, then this new token ID, we are trying to encode to get this new token ID. Most of the time it is, I mean, if it already have like 10,000 tokens, these new tokens will be the like 10,000 plus one things. But you can actually get this new token. So it try to actually encode the new token, and to check it, the new token is actually get one single token, not like, so for example, if you get a cat toy separately by a space, probably it will return 2 tokens because cat and toys are maybe very popular, very common. Maybe they will encode first. It possibly do that, but it depends on the algorithm. So it makes sure that your new token is going to be just single, actually be a single token. So get the token ID. Okay. And we get a text encoder right here. And also the autoencoder VAE from the pre-train. And the unit, of course, actually it is attention unit, and it is doing the major denoising process. And our text encoder will resize the token embeddings to get the, so that we can have a new token. So you can see that in here, dimension of each embedded factor is 1024, and we have this many tokens. So this is the embedding. We can actually get the embedding weight right here. And then we freeze everything, almost everything, except, of course, except the text token embedder. Okay, and we control our data set by using the customized data set loader. This is data loader, this is data set, and we get a data set. And the noise scheduler, we use DDPM scheduler. DDPM stands for the noise diffusion probability model. It's exactly one of the milestone paper we mentioned in the diffusion. And also there's a bunch of hyperparameters that you may refer to, because you are running a notebook. A lot of I mean, if you are trying to do a new experiment, chances are you are not setting the like a learning rate or like other things like batch size or other things right. So maybe you are going to get some training failed. They are failed training. A lot of failed training. Chances are, if you try to train something for the first time or like a few times, you are not trained successfully. You are failed in the training. But because if you are only using like doing homeworks or like using existing repos, because the hyperparameter have been already tuned, you probably will have an illusion that, okay, training is easy. We just, get some learning rate, something, and it will just work. No, it is not. Most of the time, you have to adjust the training hyperparameter, and very often you are not getting the good result at the first run. So you need to adjust it and try and see which parameter is correct. So you need a baseline to compare with, or at least you have some way to actually judge whether you are training correct, successfully or not. But here, we already have some hyperparameter. 所以这很重要，就是因为大家可能就拿很多 repo 去做训练或什么的，太熟悉了，就你觉得好，就会有错觉，就是你觉得训练就是程式跑起来就会成功，但不是，一般来说不会成功的，没有那么容易，就是一开始第一次做你就成功。通常一开始你都会有时候是完全失败了，有的时候就是像这种东西，比方说是准确率太低，然后像这种就是生的图有点太糟糕，但是你可能因为你作业做太多次了，然后拿现成的东西去跑太多次了，你会有个错觉，本来就是第一次跑或第二次跑就成功了，但实际上不是啊，失败的时候是比较多的。所以这边要特别小心的就是你在做，这边是刚好啦，这边就是因为它已经帮你都设好了，但是你做一些变化，你变化越多的时候，越有可能 会不一样。即使你现在他用的 case 是 cat toy， 你其实光是把 cat toy 换成别的东西，可能就要做一些小小修改，就有可能哦。但是不要期待说第一次一定会成功哦，就是你要先入为主，你就觉得我这已经成功，那就觉得哦，因为很多就是做了第一次实验失败，就说哦这个方法不成功，其实根本不是啊，因为本来你就不会第一次成功嘛。那所以你要有一个方法，可以帮自己看得出来，我到底成功了还是失败了啊？那有一些 baseline 会帮助你做比较容易的事情。那以这个例子来说啦，因为这个 texture inversion，所以我刚才说 texture inversion 适合当 baseline 的原因，因为它是个简单的。它其实我刚才虽然讲说很多东西不容易成功，但是 texture inversion 相对是容易成功，因为你只动一个东西，它不太容易出错。哦，可是其他的很多方法，就后面你看到一些方法不好训练，有些很多是不好训练，会容易出错。我刚才一直讲的一些东西，其实都在说明 texture inversion 是容易成功。比方说，我说那个 prompt， 你其实用5个、10个不用很多，那个图片不用很多张，你就可以得到一定成果。它其实是简单的，所以它适合当一个 baseline。好，当你在用其他更复杂的方法的时候，你其实如果没办法打败 baseline，其实就是失败了。哦，因为那些方法它动更多东西。哦，大部分这些东西的差异就是它动多动少 texture inversion 动的非常少啊，但是它已经可以得到一定的成果，它不容易让你出错，因为大部分东西都没有动到，你只是动一小部分，而且那个小部分还是你新增进去的，对不对？好，但即使是这样，也是有机会，你的东西如果说是一个比较复杂的东西，它的效果可能好或不好，它还是有出错的可能性。哦，所以这边要特别小心，就是你训练的时候不要有一个概念，就是训练很简单，训练很难哦，训练非常难。那第一次错是正常的，不是说这个方法不行，就很可能就是你没有训练好而已。好，那以这边来说，它就是 hyperparameter 都给你。Okay, so this is also something that is important because, like I said, not every hyperparameter works. So this one is very precious because it gives you a successful experiment, so that you already know. I mean, in this case, like cat toy, it works at least on this case. So if you are trying something else and it doesn't work, maybe you can start from here and to see which part you should adjust. Is the content too different? Or is the new content you need more prompt or like different prompt? So that is a start point that you can compare with. Okay, so anyway, we probably already have most of the things already get. So we are going into the actually training part. So here is the training function. We get everything here like a batch size. This is just getting things information from the config. And also list here we have accelerator. Accelerator is tools to help you to Hugging Face accelerator. This is Hugging Face accelerator. It helps you to training across like multiple GPU or making things more efficient, faster. But if you are only familiar with PyTorch, you can mostly ignore accelerator because these things would work just fine even if you remove accelerator. The accelerator is designed in a way that it doesn't modify the code of PyTorch too much. Okay, so basically you can translate the code back to the vanilla, the original PyTorch style without accelerator. So if you are more familiar, more comfortable with PyTorch, or maybe you want to debug, it is pretty easy and safe to remove the accelerator. But accelerator help you to actually if you have a multiple GPU or doing like mixed precision, it helps you to do that. So it is tools that you may be worth to familiar or feeling comfortable with it. Okay, so we also have a data loader right here, and we have an optimizer here, and we have our text encoder, optimizer, and the data loader converted by to the accelerator style. Okay, so the paradigm or paradigm of the accelerator is that okay, we don't want to do too much things. Just give your PyTorch models, optimizers, or data loaders. We then convert it into a accelerator style things, and then you can use it as usual, mostly as usual. 好，所以 accelerator 其实它基本上就是它做的事情就只有这一行，前面那一行之外就这一行，它把你的 PyTorch 的 encode 那个 model optimizer 还有 data loader 转换成 accelerator， 它帮你自动转换了。So accelerator do the things automatically for you. You probably you are thinking you are writing things in PyTorch style. So we already have like a PyTorch data set and PyTorch data loader and these models like PyTorch models and the PyTorch optimizer. You can see that it is Torch optimizer and AWW. It is PyTorch optimizer. Then accelerator convert them according to your config, so that it can run on multiple GPU or like maybe run in a mixed precision things easier. Okay, anyway, after this one, you are mostly doing it kind of like what you would do on PyTorch. Like this is a PyTorch syntax, like to some device, to some D type, and you do the evaluations mode because we are not trying to train the VAE. And they are in a train mode, but okay, they just keep the gradient, but they are not, every parameter is frozen. And here are several parameters like a number of update steps per epoch, so that it can keep the counting of each loop and the logging and the progress bar. Here are just some technical detail to make the training more like informative. They are not the crucial part or actual part of the training. Okay, here is the training loop. So let's go into a training loop. Okay. First of all, we are getting VAE from latent. So if you got an image, you first convert into a latent. So that's the first because we're working on the latent space. So here is the way to do that. But one thing is interesting is your latent need to multiply by a magic constant, magic scale. This is you will encounter this in a lot of models like stable diffusion, or maybe all of the stable diffusion model, and maybe other models like mostly it is for like latent diffusion models. But it is very often, and this is one of the common mistakes people will do. So if you encode or decode your image from the latent and see it, okay, it doesn't seem to be too correct. I mean, the color is off, or maybe it has some spatial defect like over coloring or things. Then maybe this is because your latent is not scaled in a correct way. So this scale is mostly for like normalization things. Because in the training, the latent is scaled in different things. In diffusers, you can see in the like a VAE config or things, you can get the number. You don't need to memorize this. So if you see this code, you say, okay, what the place this 0.1A215 comes from? How can I even possibly know it is constant? So you give up to actually everything, all things. But the reason it write in this style is because this is one is a quite old code, like 2 years old code. So in modern code, it will like a VAE.config like latent scale or some things like that. So you don't need to memorize this scale. This one is in the VAE configuration. You will get that number. 好，所以这个东西其实现在写法不会这样写，现在就会用通常在 config 里头。 But before that, it goes into the config. You still have a way to actually know this number. That is, go to see the source code. So because you are a programmer, you are engineer, you're a software engineer, you will. It is better for you, easier for you to actually have a habit to look inside the source code to actually feel comfortable. You don't necessarily to be feel like fun to read the code, although it won't hurt if you can have fun to read code to appreciate other people's works. That would be even better. But at least you should feel comfortable to look inside code. You don't need to feel like intimidated or like kind of feeling exhausted or like anything tired to read the code. You should at least feel comfortable to read the code. So in this case, before the things has already in the config, this if you I mean in a situation you feel like okay, when I decode the latent, it does things right. The color is off. It's not supposed to be like that. You feel something kind of not correct or not right. Then the first thing you probably should do is to go to see the issue, to see like GitHub issues, to find other people's have already encountered the same issues. But another way to do that is to look inside the source code, because source code has already, there's a pipeline, right? There's a pipeline and the training process. You can actually look inside those kind of things to find out this concept. So in the old version of this code, you will find the constant inside the code. Okay, but in the later, more recent code, in the diffusers, you will actually find these scales in like va.config. But sometimes I still get confused whether or not I should have multiple of this style or not, because sometimes it is a little bit not so clear whether or not this latent has already been multiplied by this constant or not. So still, you need to check the reference code, like in a pipeline code, or you can simply try, because we already know this is a potential issue. So sometimes you find a little bit off, the color is available or not in the perfect, not perfect. You probably will try to multiply or divide by this concept and to see what happened. Because that is really quick. When you run the encoder or decoder, you simply run the VA encode an image and maybe decode later, or maybe something like denoise things. You got a latent, you want to decode. You simply like, okay, even if you don't know the direction, I mean, whether you should multiply or divide it, you just try it. There are just like 3 different types. Don't do anything. Multiply by the scale or divide by scale. The scale is in the config. You can see like a VA config or something. You can find the scale. You just try 3 times to see which one is better. If you want to make sure, you just look inside the code because they are in the code. Okay, anyway, we got a latent, and latent, before it later has to be handled, it should be multiplied by 0.18215. And we generate a random noise, kind of like latent, because we are going mostly like add it into the latent. We get a time step from a scheduler. This one is the time step. And a noisy latent, we add the noise into it. We probably should have a Python, so I can actually go inside it. But because I haven't set it yet, and I didn't download a whole repo, so I cannot trace into it. But if you download the whole repo, I mean you clone the whole repo, you probably should trace inside this code to see how the noise is added. the way the noise is added into this data is exactly like what we describe in the how the DDPM works. We already say that it had multiplied by some constant and add some noise. The noise has already scaled according to its time step. 好，所以这边你可以进去看一下，它跟我们之前介绍的完全一模一样。哦，你可以看到这个 time step 怎么去找到它前面的那个什么 alpha、beta 那些东西，然后怎么跟它 noise 相乘，然后怎么跟这个 latent 相乘，然后怎么加在一起的。你可以完全的从这边进去。哦，但这个东西跟着它的 noise scheduler 有关。我们前面好像用 DDPM noise scheduler 嘛，所以让 DDPM 的 noise scheduler 做的事情就跟我们前面讲的东西一模一样。哦，所以你可以知道 paper 跟这边做的事情是一模一样的事情。Okay, then we use the text encoder to to encode the text prompt. So this is the encoder hidden state, and we do the noise prediction. So you can see that this is unit. We get the noise data, and the time step, and finally the condition. Here's the condition. So it has 3 different input and has one output that is the predict noise. So there are generally 2 types of output that may be used in different model architecture. One is epsilon, so that we are actually predict the noise. And the other is kind of like the denoise autoencoder. It predict the denoise image. It predict the denoise image. Things similar to that. But most of the time, it is the first time, like we described in the DDPM paper. If you are trying to use the stable diffusion, most of the time it is the first part. So you can see that noise scheduler config. It depends on the noise scheduler config. But if you are using a stable diffusion like this one, it is the first one. And the loss is simply the mean square error. You can see that there's no magic behind them. You simply compare the target and the prediction. That's it. There's no magic behind them. The only this is because we are doing accelerator. So this one is a little bit different from the PyTorch. So if you want to remove the accelerator, you should do like the PyTorch things right here. So that's it. You can see that this is a whole training process. No matter if you want to do the full training, like training everything, like UNet or even VAE, you do the same thing. You do a similar loop, and everything is already there, like the mean square error here, like the backward backpropagation things. Everything is this one. It's kind of like 15 lines or like 15 lines of code, and a lot of you can actually ignore because in this case we have 1, 2, 3, 4, 5, 6 lines, but the only thing matter is the first one because we know that it is in the epsilon case. So there's not too many lines. It's quite easy to read, and it follows the paper implementation very faithfully. But you can make sure a lot of details, like I said, the unit takes 3 input. You are adding a noise in according to the DDPM scheduler. So everything you can confirm that everything is exactly what the paper did. There's something funny like this scalar, but most of it are pretty much described in the paper. So I think the cost CP value or cost performance value is very worthy to read this code. So that's what I suggest you to actually read. Feel comfortable to read code because we only you can only read like 10 or 20 lines of code, maybe even less. And every single line is pretty straightforward. And you can actually has a full understanding and full control, because this is already everything you need to train the diffusion model. Okay, and you only need to like read 20 lines of code. 好，所以这边是非常希望大家能够去，就是既然都是软体工程师了嘛，所以读这个 code 是一定要读的。你看这个其实只有大概20行，可能更少，而且很多是废话，因为这边其实就 target noise，这其他都不重要。那有一些是你看这个 X-ray 的只是技术性的需要的东西，其实它没有一些负担的。你看真正的 loss 就是 mean square error loss， 就这样子。然后所以你还是要进去看一下怎么 noise 加进去。不过 noise 加进去跟 paper 讲的也是一样。然后有一些神奇的地方，像这个0.18215，所以这是你会记住的地方。当然其他地方你会记住，只是这个因为它太特别了，所以你会知道这个是要小心的部分。所有东西你就是读完 code 就行。I can imagine that if you are very unfamiliar or start to read this, you will feel kind of discouraged by, I mean, what does this mean? I can read 1, 2, 3, 4, 5, 6, and I don't even know what it means, and I'm getting nowhere. I'm just getting a bunch of config, but most of the programmers are not trying to confuse you. So everything like training, batch size, gradient accumulation, learning rate, they are exactly what it means. So these lines can be skipped, mostly skipped, or you can like read them really fast. And I can imagine that if you are not familiar with accelerator, so you will feel very discouraged. Okay, what does it even mean? Like accelerator, and you might will be stopped right here. But yes, this is true that accelerator is something like overhead when you read the code. But accelerator is just one thing. You will encounter it a lot of time, and it is one-time thing. If you already know, like what I explained it to you, what accelerator is, it is just the accelerator. You can pretty much ignore it because everything else is PyTorch. 好，所以前面这一段当然就是你可能会停在这边，因为太长了，又不知道干什么。但是你基本上相信那个作者不会骗你了，所以这每一句其实差不多就只是一个等号嘛。所以这部分你知道它的意图只是要把东西读进来。那 accelerator 是一个比较真实，就是它是额外的东西，没有错。但是你会碰到很多次，所以你就碰到一次，而且我已经跟你解释了，就是 accelerator 就是它只是一个很薄的一层，它会自动化帮你模仿 PyTorch 去做的事情，它只是一个工具，你完全可以忽略掉它。然后其实很多东西都是杂讯，然后你知道它意图，它这意图就是因为你必须要 optimize， 它不是故意要让你觉得怎么看那么久看不到东西，但是你总是要有东西把 optimize 弄出来嘛，就是它就从这边拿个 optimize， 然后都是必须的嘛，这个 accelerator 就刚才这个东西嘛，有个 accelerator 对吧？前面这边这个东西 accelerator 就是它的一个固定招式，对，差不多就是固定的。所以真正要读的，其实我们说简单，是因为真正要读的只有在中间这一部分而已。这部分其实很短。这个地方其实也会卡住了，因为一开始不是很确定到底它是 epsilon 还是 free prediction 的时候，看起来就是1、2、3、4、5、6，后面两个可以不重要，但至少这边至少2种 case 嘛，感觉有点复杂。所以这边比较像是追踪的技巧。我第一次读到的时候就去稍微追了一下，发现它的情况是 epsilon。那就而且试了好几个，几乎大部分 schedule 其实绝大多数都是 epsilon， 所以后来我读到的时候，这边就变成不是负担了，因为我知道大部分都是 epsilon， 就是大部分。那其他的情况就是你要这 config 你去追踪一下，你就知道它到底是哪个东西了，确认一下，就稍微确认一下，你找个地方把这个 schedule 的 config 把它印出来，或者看它 code。Okay, so this is how we read the thing. So this is the whole training process. We're taking more time on this or more detail on this training process is because essentially this is the diffusion model training process. So although we are focusing on textual inversion currently, but all other things like Dream Boost or everything like LoRa, even like control net, they are essentially the same. So we are looking more details into it. Okay, so that's pretty much the things I want to address is the training loop. Everything else you can actually read them, but most of them are not too important. Like this, he just load the trend things from the checkpoint and do some testing. That's it. Okay, so let's go back to the note here. So here is a texture inversion. So you can see that this is a very early attempt, one of my very early attempt to do the texture inversion. It is not doing very well, actually, because the one of the things I didn't do correct is the aspect ratio. So another thing you need to look into is the data set, the customized data set, to actually check the aspect ratio of image. So the thing I didn't do correct is the aspect ratio. Because it has do something to handle the aspect ratio, and I didn't realize it on the image I corrected is not in a perfect suitable aspect ratio for that kind of process. So you can see that the aspect ratio is a little bit off. So the later I later experiment has fixed this, but I was showing that something that I did first for like texture inversion. So another way popular to do that is called the Dream Boost. But the Dream Boost is simply pretty much similar, except it didn't do. It can, but usually people doesn't do the texture inversion part. You can do the Dream Boost things with the texture inversion. Uh, Originally, Dream Boost is developed by Google applying to Imagine, but they are using it on people using it on Stable Diffusion a lot. And the notebook you are seeing right here, the training notebook here is probably you are going to use for homework, reference for homework, is doing it on Stable Diffusion. Okay, so what is Dream Boost? Basically, when you do the fine tuning, you are this is your output. Your you have a similar thing like okay, kind of like texture inversion, like this kind of different things. But you are training on your unit instead of training on the texture inverse. I mean the texture encoding. So that's it. That's it. You simply the for what the Dream Boost is that you're actually training the your unit. The difference between the Imagine, that Google diffusion model, and the Stable Diffusion is that the Imagine does not using latent. So instead, it uses a super resolution kind of model. So it has a super resolution thing. So the Imagine, I mean the dream or the original Dream Boost actually doing on different unit. But for like Stable Diffusion, we only have one kind of unit, so it makes it much simple. So let's check the code. Hopefully, we can check the code right here, but not exactly. So we still download the notebook. Let me still download the notebook and open the notebook. Okay, so here is a notebook of the Dream Boost. So you can see pretty similar. It downloads several things and get some like Xformer things. It also uses accelerator. Everything is the pretty much the same. And this is a utility tool. And they are using Stable Diffusion. Here they're using Stable Diffusion 2 model right here. You can use other things like Hw4 or like 1.5. They are also uh, they are also fine. Okay, so here are just they are also using the cat toys things right here. So again, you don't need a lot of images, but you can use a lot of images. You can use in this method. It is actually if you have like 2,000 images, that is still works just fine. But in this example, they are still using a cat toy things. Okay, so their instant prompt is like a cat toy. They are not trying to manipulate or mess up with the text encoder. So this, although we still see something like a new token, it is not a new token. It's just a special kind of phrase. It doesn't matter if you can combine it with the textual inversion to make this a new token. You can also do that, but you don't have to. And in this example, it doesn't do the things. So the example, the special part of the Dreamboost, basically Dreamboost is just fine tuning it with unit. It only modify with unit. But the key point of the Dreamboost is that it wish to maintain some negative sample. So instead of like a cat toy, this is cat toy, and there are something like other kind of cat. Like if you want to add a new concept of a new a special kind of dog, you probably doesn't want to it mess up with the concept of the toy. I mean, in this example, it is a cat toy. We want to make sure that cat toy is referred to this specific type of toy. However, if you train it directly, one situation is that the model will treat every toy. If it encounter in a prompt a toy, it will generate something like this one. But if you want to not only generate this type of a toy, but also other type of toy or other type of maybe the cat play toy, you are trying to collect a negative sample data set that is not this kind of type of toy, but they are still toy, and you use a negative. I mean, you don't use a special word right here. You still use a common, like regular description, so that the model can not only generate this special type of toy, but also it preserve the original capability to generate other type of toys. Dreamboost 其实现在当然大家就只是讲它做 fine tuning 了，但它在 paper 里头有一个重要的一个东西是，它特别讲的是它保留其他类别 negative sample 类别的东西。那只是现在讲有时候不是那么注意啊，但是它的重点就是，好，比如说你现在要生这种特别的玩具嘛，那我们现在又没有 texture inversion， 所以我们用的是这种 cat toy。好，那所以它有一个可能性就是，它之后只要碰到 toy， 它就全部生这样子。好，就像说我们要生某一种特别种类的狗，那你训练的时候一定是拿那个特别种类的狗当做训练集嘛？那可能最后变成只要碰到狗，它就生成那种特别种类的狗。可是如果这是你不想要的，你要想它保留原本训练，就生成其他种类狗的能力，只是你加一个特别的关键字的时候，它可以生成你要的狗。如果这是你很注意的方向的时候，那你就要有 negative sample， 也就是说，除了正向的像这种 cat toy 以这个例子来说的话，你还要有其他的玩具啊，你不希望 toy 也被污染到了。 所以你就要有其他的玩具，然后你用其他的句子去生那些其他的玩具，在训练的时候同样做这件事情，那这样它就可以保留生其他拓野的能力，然后你要给它这种特别关键字，它就会生出你特别要的东西。所以这是他那个 paper 有讲到一个比较，因为如果你只是 fine-tuning 那个 Unet 没有什么嘛，但它重要点有一个部分在这个地方。他刚才那张图其实也有讲这个事情。Okay, so here are some hyperparameters also for the training. This is data set. It's pretty much similar. You load the image and the text prompt. If you have a negative sample, like we said before, it will incorporate with the data set. I mean the positive image and the negative images. Okay, so pretty much the same similar sense, except I mean it also load like the text encoder, VAE unit, tokenizer, load everything. All the hyperparameters, and it also has a accelerator. It will convert everything into the by using the accelerator. You can see that optimizer right here, data set right here, data loader. Okay, here. So you can see that every depends whether or not you're trying to train the text encoder. Like I said, optionally you can also train the text encoder, but you don't have to. But anyway, you will like using Excel prepare to convert everything like unit, optimizer, data loader, or maybe even scheduler into something compatible with accelerator, so that you can work on multiple GPU and maybe faster. So everything else is the same. Here is also the training loop. As you can see that we have exactly the same like VAE encoder and latent multiplied by a scale. And we have a noise, and noise is added into it. This is noise latent. We got the encoder here that's the condition, and we feed everything into the unit and get the prediction. As we can see that we have an epsilon case, so our target is noise. So we compare the unit like here. But if you have a want to preserve like this prior preservation, you do a little more things like other negative sample things. But if you are not too worried about it, it is exactly the same. It is exactly the same. Just use the mean square error. And here are just technical part for an accelerator because you have to sync your gradient, things like that. So that's it. The only thing different is you have to check whether or not if something is frozen. But I mean, the training loop is pretty much similar. So you need to check like which part is frozen. Maybe you should check the frozen. Okay, we're not trying to find it, but let me check the whether when the model has been loaded, and we can trace like here, the unit has been loaded right here, and the VAE loaded right here. So we should compare at least VAE and the unit things. 好，所以其实它的差别就是在于它有没有被设定成可以被那个训练。So you can see that the VAE requires gradient is false, so it doesn't require anything to be need a gradient. So we are not training the VAE. And the unit here at least if we are gradient checkpointing, so it enable it. But as you can see, it is not setting it to be frozen. But here, our required gradient is right here. But mostly, I mean, it is the for the optimizer. We're getting to see the parameters like here, parameters to optimize. So you can see that we have a unit parameters. If you want to train the text encoder parameters, you will get here. But if you are not trying to train the text encoder, you can only there's option that you only train the unit itself. So whether or not it depends whether or not you want to train the text encoder. So if you are not trying to train the text encoder, you are only train the unit part. So although it's called Dream Boost, basically there's an option that is quite easy. That is, you just run the training loop and you train the unit. Except, I mean, in the paper, like I said, it is kind of emphasis on the prior preservation. That is, you should preserve the variety of the original word. I mean, original general category, like the whole toy things, or like if you want to train a special kind of dog, you are actually wanted it to preserve the ability to train every dog. But I mean, most of the time, our goal is to train to a certain style. We probably doesn't care that much because we want to, for example, you want to generate a Ghibli style of images. You probably doesn't care too much about whether or not it generates other type of style. If you want to generate like kind of like a Disney cartoon, probably that is your purpose. You probably doesn't worry too much about preserving things. So you should just for the very vanilla, very basic setting, you only train the unit. But in the paper, it kind of emphasis on the things that it on the negative sample things, and also it kind of like common sense that you have an option to train the text encoder. So it only depends on you whether or not you want to train a text encoder. Because text encoder is relatively smaller, so it you can train them both. If you want to train only the new token, it is also doable. So it really depends on whether you want to what you want to train. But the training loop is pretty much the same. And the good thing is you don't need too many images to train. And the training time is kind of you don't need to take like weeks or months to train it. It can be trained really fast. So because if you have only like 10 images, it doesn't make sense to train it more than like 2 or 3 hours. You probably only need to train it like several minutes. And if you see the result is okay, then that's it. 好，所以这个训练其实都很一致啊，就它虽然不同名字，什么 texture inversion、dream boost，但基本上是一样的训练回圈。然后概念就是我要挑哪一些部分来训练，那这两个部分就都没有碰到。Okay, so if you kind of straightforward or like apparent question is, okay, can we also train the variation autoencoder, or can we just train the variation autoencoder and keep the unit or texture encoder frozen? You can do that. You can do that. You can train all of them. Every possible choice. I mean, every part can be frozen or like do you train. They have some different name. Like one of them, if you train like the everything is maybe called the pivot training. But in fact, I don't even bother to remember all these names, but because everything is doable, and if you should try it for a few images, you will build up the experience of and the expectation of what would it be like if you see the data set, and you can imagine, okay, if I fix the unit, I mean, if I fix the VAE and train only that unit, what kind of result I can expect it. Usually we don't, I mean, if the For me, VAE doesn't change that much. I mean, you can in fact do a simple experiment to, I mean, if you got one like JoJo style image, you can do the VAE to do encoding into Latin and decode it back to the original style. I mean, it is an autoencoder, right? So if you do the encoder and the decoder, it will return to an image very similar to the original one. If the differences is acceptable for you, you think they are, you don't care. You probably will see some differences, but if the difference is not too significant for you, probably you don't actually need to train a VAE at all. But if that differences is important to you, it has never happened to me most of the time, except for very low resolution image. But most of the time, if it is higher resolution, like high enough resolution, it never bother me for the small difference between, I mean, for a VAE. So if that is not the case, you probably all you need to do is to train the unit. It would be easier to train. 好，所以重点就是那个，你可以简单测试一下 VAE 是不是已经够用了嘛？你就把这张图片，你要的图片，先 encode 再 decode 回来，它会有差别。但那个差别如果你觉得不重要，就不重要了。啊，它会有差别，然后有的时候那个差别会还蛮明显的，有的时候了，那就看你的。我自己是没有，有些人会有审美观，还蛮厉害的，他会觉得那个，因为你会看到很多人有自己客制化的 VAE 嘛，有很多，那显然就是在审美上面有差异。那如果那个东西差异是你觉得重要的，那 VAE 你就要去训练。那大部分情况下，我觉得像这种 Unit 直接动一下，其实就可以了，因为很多甚至只有 low run 嘛。那这个东西的话就，我觉得是，就是这个因为训练起来很简单，然后也够用啊，所以如果你要客制化一个模型，你就直接动 Unit 其实是不难的事情。好，那只是说你完全有选项，把 VA 也动到，Texture Inversion 也动到。就大部分其实我觉得就动到 Unit 跟 Texture Inversion 这两个就够了。因为 VAE 就是我刚才讲的，如果你的 encode 再 decode 回来，你觉得那个差距是你可以接受的，那大概它就不是很需要去动它了。不过你都可以试试看就是了。OK OK so that is the Dream Boost. Let me share the screen here. Okay. Our homework here is for ask you to do the Dream Boost things. The only thing you need to change is create your own data set and then fine tune a stable diffusion model using the Dream Boost method. Although there are more recent model like Flux, High Dream things, we probably stick with stay with the stable diffusion because they are still available. You can use stable diffusion XL if you really want, but like anything like 1 point thing, 1 point something, 2 point something, or stable diffusion 3. Maybe stable diffusion 3 is also fine, but stable diffusion 3 is a little bit different than the previous models. So maybe you probably should stick with like 2 point something, 1 point something, or SDXL. But feel free to use the stable diffusion 3. But only that I have only tested. I'm pretty sure they can work very easier to do the fine tuning on all these models, and there will be some. You can find the instruction or notebook on them, but you will have to modify and choose your own data set. That's a key point. You can use the notebook, existing notebook, and the purpose of this one is like you actually understand the details of everything because already, although we have already kind of given a brief walkthrough of the code, there's nothing you can replace. You actually run the code and understand step by step by yourself, and running the code, you can do some experiment. There's nothing can replace that experiences. So you should do that with your own data set. You can do this for the first round. You can do that with their like KTOS or other data set that have already provided as example. You can do that, and I suggest that is a recommended way that we. So you can do that. You do not do it too fast. You don't to be overconfident of your ability. The first step you try is you just follow the example exactly. At least you know something as a baseline step. Then you change to your own data set and to see what happens, so that you can compare with the example. So you have an idea what is success and what is failure. 好，所以这边基本上就是换成你要自己的 data set， 然后当然建议你一开始就先照着它的 example 没关系，因为不会跑很久了，然后后面就照你的方式。Okay, so there are some rules that I put right here, like here. So for detail, but basically the only purpose, the major purpose is the primary purpose is to at least you have the experience to do the fine tuning, which is not too difficult. To build up an experience of what would happen, of and how difficult and how effective this fine tuning could be. Okay, so here are some requirements. Of course, one thing I need to emphasize is that you need to actually show the prompt you actually created and how you test your fine-tuned model. 所以一个重点是你要告诉我你怎么设计你的资料集。So the data set is the whole point of these things. Because in the instruction, it is kind of okay allow you to use existing script, but there are still something you can adjust or to have freedom to do that. The most things that you can adjust is the prompt and text pair. You should describe what the data set it is, and try to show that okay, does your model generalize to other prompts? So you can actually try it. Either it's success or not. It doesn't matter. But you have the experience of okay, how far this prompt can go to or can be generalized. 所以重点就是你要先知道，你要能够很确定你的资料集长什么样子，然后 image 跟 text 是怎么去配对的。然后你可以测试，就是你可以用类似的 prompt 去生图，什么什么东西 in 什么 style， 但是也可以做试试看，把它稍微变化一点。像那个刚才看到它放在那个涂鸦墙上面嘛，但是在训练集里头没有。所以你可以试试看这件事情。所以这边你看 ，so you can see that because we are focusing on data set and how the generalization it is. So you should show at least 10 sample images generated by the resulting models and provide some creative prompts to see how well the model generalized to a prompt that does not exist in the training data or like a training template. Also, that's the whole point of this homework. Okay, so these are some popular methods to do the fine tuning. There are even more. So basically, you can see that the first two is just training, but we've frozen many part of it and only training part of it. For texture inversion, it only we are actually doing something to modify the architecture like kind of expand the architecture a little bit。好，所以基本上就是 frozen， 然后去大部分的地方，然后去训练一小部分。那 texture inversion 甚至说它技术上还把那个 embedding 那层 layer 把它扩展了，只有做一点点事情，但是这个也算是改了它的 architecture。And there are other ways to do fine tuning and popular. First of all, is LoRa. LoRa is one of the here is the paper. Okay. This is control net. Okay, LoRa right here. So LoRa, what is LoRa? LoRa is called the low rank adaptation. Low rank adaptation. And the LoRa is actually invented with language models. Originally, it is invented with original models, but it used a lot to fine tuning image models. So first, let me show you what the LoRa. Okay, let's just see the image right here. So basically, what the LoRa is. So we have a lot of like linear matrix, linear transformation in our models, even like in large language models or in other like in diffusion models. There are a lot of linear part. All of this linear part are considered to be huge, because they are like a 1000 by 1000 matrix, so they are kind of huge. So if you have a 1000 by 1000 matrix, you will have like 1 million parameter in this single metric. So when you do the training, if you have a lot of parameters, it will take time and difficult to actually to optimize that many parameters. So can we use something like parameter efficient fine tuning? Since this is called the PEFT, parameter efficient fine tuning. So can we use a smaller matrix? Can we only fine tune some part of the parameter instead of all of them? Yeah, that is exactly what we did for like Dream Boost or like the that is exactly what we do for the Dream Boost or like texture inversion, right? We frozen most of part and only fine tuning only part of that. But in this case, it might be a little bit restrict because we only train part of them. I mean, when we do a fine tuning, like fine tuning the YOLO model or other image classified model, it is very common way that we frozen a lot of layers and only fine tune like the last 2 layers or first 2 layers. It's a very common practice to do so. But in this case, we may wonder whether only fine tuning the last 2 parameter. I mean, the parameter of the last 2 layers is enough. I mean, for every layer, they have functionalities. If we will only fine tune the last 2 layers, it's possible that we miss something, miss some potential of fine tuning things. Then, so in fact, it is usually you will usually get a better result if you fine tune the whole models instead of just the last 2 layers or last several layers. But still, if you want to fine tune the whole models, there are a lot of parameters that is you need to adjust to do the fine tuning. So it is still kind of taking time, or maybe you need a lot of data. So is it possible that we only fine tune a little bit of the parameter, but we fine tune every layer? Certainly, there are some methods to do that. So for one naive way to do that is you can actually randomly select some of the parameter. Like, I mean, if one layer is like 1000, there's one layer we have a 1000 by 1000 matrix. So it has 10, like 1 million parameter in this single metric. Can we just randomly select like 10% of them to be adjustable and frozen like the other 90%? Then we are kind of evenly training all layers, at least in a certain way. Can we simply do that? Yes, we can do that, and I think that is a pretty reasonable way to do that. And there may be some variations, like, okay, so for the first 10 epoch, for this layer, we train like 10% of them. And for the second epoch, we train another 10% of them. So at each moment, we train only part of the models. Or maybe we just fix 10% to exploit the power of randomness. So maybe randomly 10% is enough. Although this method is kind of reasonable, I haven't seen people use this. Probably because of the technical detail. Because if you wish to kind of frozen like 90% of one matrix, it is a little bit difficult and maybe inefficient to do so. You still need to keep track something like back propagations to keep things. Maybe you didn't save that much, but although it's seemingly kind of reasonable, but I haven't seen people actually do that. But certainly, what I mean is, there are ways. Certainly, there are ways to train every layers and using less parameters. And another thing is there are better ways to do so. One way is just the LoRa. Here you can see that. Okay, we have a really big pre-trained weight. We want to only train like very few parameters, but apply our adjustment to this weight. But we don't want to train like suppose this D is 1000. So this has 1 million parameter. We don't want to train whole 1 million parameter. We want to kind of modify this matrix, but we don't want to adjust that many parameters. So one way is to, okay, we still got 1000 by 1000 kind of matrix or like a linear transformation from dimension 1000 to 1000. We can still do that. But we restrict ourselves to a low rank metric. So we can use very few parameter to do that. OK， 所以我们这边用的就是 low rank 的 metric。那这个 metric 你可以想象它的大小还是展开之后的大小还是那个1000乘1000，总共100万个 parameter。但实际上它可以分解成2个。So we kind of do a decomposition of this 1000 by 1000 matrix to 2 smaller matrix, like 1000 times maybe 100 or 100 to 1000. So if we multiply these two matrices together, we get a 1000 by 1000 matrix. The catch is that in general, we cannot compress or decomposition 1000 by 1000 matrix into 2 smaller matrix. There's no free lunch. So in general, you cannot do that. If we can do that, then everyone will do that. And there's no like 1000 by 1000 matrix exists. So in general, not every matrix can be decomposition into 2 smaller matrix. The multiplication with 2 smaller ones. only the low rank one can do that. But we probably don't need the full power to do, because we are imagine we only do a slightly modification. So we are restricting us to a special kind of metric that is only low rank. So that's why with this kind of thing called the low rank adapter. 好，所以一般来说，1000乘1000的 matrix 你就需要100万个 parameter， 就是资讯没办法压缩了。但是如果我们只考虑一些比较简单的 matrix， 我们可以把它变成1000乘100的一个 matrix， 乘上一个100乘1000的 matrix。那这两个 matrix 乘起来，你会变成一个1000乘1000的。只是这个东西不是一般的 matrix， 它只是一种比较简化过的。所以如果你以线性联立方程式，你可能有3个未知数嘛，你用3个方程式可以解出来。一般来说，3个未知数用3个方程式可以解出来。但有的时候你会发现解不出来，因为有2个，比如说你用其中2个可以凑成第3个。那这种情况下就是一个比较特别的，它的资讯比较少的。这种东西就是 low rank 的意思。因为如果你有3个未知数如果你有100个未知数，然后有100个方程式，一般来说它都解得出来，因为它的资讯够，你可以解得出来。但是如果你是一个比较特别的联立方程式，它中间资讯量不够就是可能其中20个是独立的，剩下30个都可以从20个凑出来。那这种情况下，我们称那个东西的 rank 是20，它的 rank 是20，它不是真正的1000，它只有20。那在这种情况下，它那个东西解不出来。好，所以你可以看到，就是某一些情况，它有一些特例，它是一个 degenerated 的情况。那一般来说，1000乘1000，你随机的一个矩阵，它的 rank 就会是1000。但是如果我们只考虑一些退化的一些状况，一些 degenerate 的状况，比如说它 rank 只有100的那些状况，那我们就可以用更少量的资讯去表达它。Okay, so in general, a random matrix will have a rank like 1000 by 1000 matrix will have a rank 1000 in general. But if we only consider that the degenerated case, like a matrix only have a rank like 100 or less, then we can use less parameter to represent this matrix. So for example, if we only consider a rank of matrix like 100, we can only use 1000 by 100 and 100 by 1000. These two metrics to represent a matrix that has only rank 100. So that's the point. We are using less parameter to do adjustment. What we are losing is for the general case, we are only consider a very limited and special kind of variation. So we are losing the full power of doing the adjustment. There are certainly certain kind of adjustment that is not achievable by this type of low rank adaptation. But on the other hand, the pre-train, we are assuming that the pre-train weight is already pretty good. We only need to do some local or small adjustment. So we are hoping that the low rank adaptation is enough. So in particular, the formula is kind of looking like let me to go here. I'll hopefully see that it has a mathematical formula here. No? Oh yeah, okay. The idea is that we are assuming the original W is already a pretty good. We only need to do slight adjustment. So that is called delta W, meaning this one is small in certain sense. There are many different sense of smallness, like the value, the maxima value and the minima value should be very close to 0. That's one sense. But another low rank is also another way of saying this adjustment is small. So we are choosing low rank because it is easier to do that. It benefit for the technical reason. And in fact, low rank is very common. It is not just we are choosing this for merely technical reason. It is actually common to represent small things by low rank things. So anyway, this delta W is small, and we are choosing it to be low rank. So our new W, new matrix, can be considered as W plus the delta W. But because the delta W is small and low rank in our sense, we can actually write down it as a decomposition like AB, like two smaller matrices. The first one is like M to D and like M to D. And the D is very, very small, much smaller than N. So the total parameter it needed is originally it requires like N times M, which is quite large. But in here, it's like M times D plus M times D. So in our example, if our N is 1000 and the D is 100, so A only requires like 1000 times 100, which is like 200,000, 100,000. And the B is also like 100,000. So totally we need only 200,000 parameters. But the original one needs 1 million. So we only use 20% of the number of parameters. So that's how the this kind of low rank decomposition saves the parameters. The original W, we still keep it because we already have it. But the only additional information is like only 20% of the original one. So you can actually add them together to be one. I mean, if you keep the the delta W and W together, you are totally require like 120% of the storage to store all the information. So sometimes we kind of merge or fused them together to get, you only need like 100% of the data storage to store all the information. If you are consider the final result, you don't need worry about the original W. You are not never going back to the original W. Then you can get this W prime instead of this. But a lot of time you can see that we have a base model like W already have it, and we store we save the LoRa parameter in a separate file. So it is smaller, much smaller than the original one. Then we load them both, and we fuse them or merge them in the memory on the fly. Okay, so because they are all linear, so there are two different ways to do that, to do actual inference. One way is like this one. You simply add these two matrices together to get a W prime, and use this W prime to replace the original W. That's one way to do that. The other way to do that is you put your input into a W and get an output of the original output, and you run this one again, like X, to feed into B transpose, and then feed the output to the A to get the output together. You get another vector. So in this way, you get another vector, then you add them together. So that's require like more computational power, but you can track all the what is the original output and what is the modified output, or sometimes it has a benefit. Okay, so in like attention, you have the KQB, like since attention layer, output things. All of this can be doing using LoRa, and you can combine these LoRa things with stream boost because the unit has a lot of linear part. For texture inversion, there's not much because only get one vector. It is not like a 1000 by 1000. You get only 1000. it is not that much. But if you are training, fine-tuning the whole text encoder, it is doable. But in this case, it is not that much. Okay, in the pivotal tuning, which is actually doing, training everything. Training everything, then of course you can use in LoRa. Okay, so this is one of the implementation of LoRa. But if you want to do it with the diffuser, okay, there's a library called the PEFT, Hugging Face PEFT. It will do a lot of things automatically for you to actually add the PEFT like LoRa. One of them is LoRa, and there are also others in like IA3. Basically, most of the time we use LoRa and sometimes use other method. It has some variation like quantizations or mix adapter things, but you can use the PEFT. So if you are trying to add a LoRa training, fine-tuning on a model, PEFT is the way to go. Currently, PEFT is what is a way to go, especially if you are working with a model that in like a transformers model, Hugging Face transformers model, or a diffusion model. So PEFT is a way to go. Okay, so this one is the LoRa. Control net is kind of similar to LoRa things. It also can be considered as a plugin or add something into it. Control net is designed originally already designed for like stable diffusion in mind, but it is a more general framework, can work with other type of things. So suppose we have a neural network block. Mostly it could be anything like convolution or like a linear or dense or anything. Mostly for like convolution. It consider that things like convolution. So basically, what we are doing is kind of like a LoRa. We add things into it. But our primary purpose is not to reduce the parameter. We are trying to add some new condition into it. Okay, so before that, let's first see what control net is. The primary purpose of control net is to doing some image conditioning. The original for the stable diffusion, the condition is, we only have one condition, is the prompt, the text prompt. So it doesn't have the ability to add some image as condition. So why we would need image as condition? So for example, like coloring things. So if we have something like this one as input, we may want to generate some image that is related to this one, but it has color or other things. So this is one example of things. Here is also we have some kind of edge detection. We have some edge map of this image, and we can generate some variations to this by using this as input. So we can change the color of this dog, change the background. But this one is mostly a dog. If you want to change it to a wolf, it is also possible if you do a different prompt, or maybe you can make it like a metal one, like a robot dog things. It is also doable because it will follow the text prompt as well as this like edge map. And also not only for edge map, you can do things like this. This is called MLSD. It's like a straight line detection, kind of like an edge map, but it only follows the straight lines. It's mostly useful for like human-made, man-made structure like the rooms or the things with a lot of straight line. So you can get a lot of straight line right here, and it can fulfill the image into like a decorated room, or like this one is also for a straight line, but there are also like other type of um edge detection things, like change human style. This one is also HED, like edge detection things, or like maybe you can like hand drawing things. If you have enough data set to do a training, you can do like making a hand drawing into photorealistic photos, and kind of like this one. And also there are like segmentation maps. These are more like the edge detection things, but they are okay. Human pose. You want to control the image generation by certain pose. You want to the people in your generated image to have certain pose. Then you can use a pose detection map like this one to control your output. Okay, and this one is like a semantic segmentation. And you give a rough idea. So you can imagine that you have a painter. 你有个小画家在这边，你可以自己画图。So you can paint the basic things and generate something like a house or like a forest based on your design things. This one is kind of like reversing. And another popular one is the depth map. You get a depth map. You generate according to its depth. This is one of the favorite conditional input I use a lot. I'm mostly using like pose and depth combined with. I mean, one of the favorite is the depth, because you can use like Blender or other 3D modeling to get a rough depth, kind of like a rough depth images like this one, and you can even modify it a little bit, and you have more control than like the semantic segmentations. This one is kind of too. This one is also fun, pretty fun. You can try it, pretty fun. Like drawing human or things, it's pretty interesting. But if you want to control things more precisely, but not too precise like the edge map, it was too similar to the original one. But you can see that even though this one has a kind of a spherical head, but you can change it to other type of face. So I personally pretty like the depth map, because it mixes up with the controllability, and also you have some freedom to do the creation. And also another thing is similar is a normal map. Normal map probably even more popular than depth map. It's just I use depth map more, but normal map is perfectly fine, and you can do similar things like a depth map. Okay, also like coloring or like super resolution or denoising things are all like the possible application to this kind of image conditioning things. The control net is doing this kind of things. The only things that the primary goal to achieve these kind of things is to let the stable diffusion recognize or aware of this image input. There are several different ways to do that. One way is you probably can do is to embed the image information inside the text prompt. Because the text prompt is already inside the control net. I mean inside the stable diffusion architecture. So you can somehow smuggling the information, or like kind of injecting the information of this image inside the text encoding. You can add on. I mean, after you do the text encoding, you get a text later. You can add or concate this additional information inside this data. That is doable. But that is actually doable, but we probably will kind of afraid or like worry about because the text prompt is already kind of full of information, so there probably doesn't have enough room for the other information like image, and they will probably mix up and get things worse. That is still I mean a doable things and very reasonable to try, and it will have pretty good result. And you have, in fact, more freedom than ControlNet it is, which we will talk about the limitation it has. But ControlNet is also another very popular way to do that. Okay, so what ControlNet does is kind of like LoRa. You add things to the original one. So this is X. Originally, we have like a denoise block, like input, like a latent. This is more like an image latent. And we pass through this neural network and get the output. So instead of this one, we add a new layer alongside with it. So here we add the condition. First, you just ignore the zero convolution at the beginning. We add the image condition here. C is the image condition. We add this image condition and the original input together. This one is actually the addition. We just pixel-wise add them together. So they will have the same dimension, but we simply add them together. And we feed them into a copy of these similar things and get the output. So the output will have exactly the same dimension because in a diffusion model, the dimension of X and Y are the same. So that makes a lot of sense. But I mean, in general, X and Y could have different dimension. But anyway, because we have a trainable copy, so we can, if you ignore the zero convolution right here, we will have exactly the same dimension as the output. So we can add them back to the Y here. So if you ignore the zero convolution, the idea is pretty simple. We are training a parallel copy of the original one. We are using a trainable copy to kind of like initialization, not the random initialization, but this is not a crucial part. You can use a random initialization. It's just difficult to train. But anyway, the goal is to train another layer alongside with a frozen fixed original one. And this one can be considered as a plugin. Okay, so we are adding. So how does this new information come? We simply add the output, the input with the conditional. We add them together and fit them into the parallel block and get an output. And we use this output to modify the original output. So we still have the original X and output, but we have a plugin or like a kind of like a customized. We can just call it a plugin. And this one is similar to the original one, except it is aware of the conditional input. So in this way, if we combine them together to see them together, it will become a new block that not only take the X as input, it also accept the condition. So the only technical detail and the part is that if we are just simply get a trainable copy, a trainable copy is very reasonable because it is at least it is something that has been already pre-trained. Although it has never been exposed or like trained to aware of the input, but anyway, it is much better than a random initialized thing. So it doesn't. It's just a choice. It's just if you are better pre-trained things, have the same shape. Feel free to do that, and it doesn't exactly need to be have the same shape. It can be like a LoRa model or things, but it's just easier to have this one. But the thing is, at the beginning, no matter if you are using a random initializers or a channel copy of this one will modify these things too much. Remember that we have a lot of different layers. So if you actually mess up with these things too much, the training is going to be very difficult because it will get confused and it will change the things. So maybe it is very difficult to converge. So we prefer to at the very beginning, we wish it to kind of doing minimize or nothing at all, and we change it a little bit. So we start with, although we give it condition, we can allow it at the beginning. The condition doesn't kick in too much, but at least we wish it to generate some kind of okay image. Then we change it a little bit. Our strategy is, okay, maybe you can design these things to have zero effect on these whole things. But after we do the training, it will change a little bit by a little bit. That is our hope or our imagination of what it will happen. So how do we actually make the initial things to be zero effect? Also, that's how the zero conversion does here. So, so for the output here, because it is a zero conversion, it is a conversion. It's just a conversion, but initialized with zero things. After the training, it will not become zero. But at the beginning, it is a zero conversion. So no matter what you did right here, the output is going to be zero. So although we add the output right here, at the very beginning, it will not change this output. Similar to this input things, because we have a zero conversion right here. This conversion is supposed to be kind of something like an adapter to adapt the condition input into something compatible with this trainable copy. This is we need some conversion right here. We don't actually need too many. This conversion is not necessary by design. I mean, because this is going to be trainable things, we don't need to have things to be compatible. It doesn't need to compatible with anything. But still, a conversion can be considered as an adapter to transfer or to convert the output into another space. That is similar, but maybe it fit into a subspace of this output to modify this output. But anyway, this is necessary because we need a zero output, a zero not effect to the output. So it is an easy choice to have a zero convolution right here. But here, no matter whether you need a zero convolution or not, you need a convolution to actually adjust because they are in a totally different latent space. You need to do some adjustment to project these things into something comparable with this input, or at least they can add them together. You need something here. But we use zero convolution so that at the beginning, because this is a trainable copy, it's very logically reasonable that it take X as input. So we can use X as input right here without any issue. But at the beginning, we should be very careful because we don't know what it is. We don't want to mess up it too much. So we have our C right here. And at the beginning, it has zero effect. Then we start by doing some training. This zero conversion will become non-zero. And it will become something like an adapter to adapt this conditional things into something compatible with X so they can add them together. 所以这边就是一开始都小心一点，你就用零刚开始的时候，因为我们要转换嘛，那一开始你用零嘛，然后慢慢动，就是先不伤身体，基本上就是先不伤身体，然后再讲究效果。所以这是一个还蛮合逻辑的设计。So this is a very reasonable design. Everything has its reason. It is not the only one way. It is not the only one way. There are some options that you can change. For example, you don't need addition. You can use like concat. But of course, this copy, you probably need an adapter right here, or maybe you can change this trainable copy a little bit so that it can incorporate with additional input. That is a pretty obvious or apparent option to do that. And you can use something like random or zero things similar to this one, but expand this metric. 所以有很明显的一些其他选择啊，就是你可以把这个做个修改，让它增加 dimension，所以这两个 concave 在一起。那你可以做一些修改，让它一开始的那个不要影响到。但是 zero 的话会有一点点麻烦呢、因为全部不影响的话，因为它全部都 zero，它训练起来你会需要一点点 randomness。那你可以用小的比较小的 randomness 就够了。所以你可以用不要完全 zero，你用个小的非常小的一个 randomness，但是把这个 metric 做个 extension，让它吃更多的 input，完全可以这样做。但这样比较简单。But this design is okay. It's pretty reasonable and simple, and it actually works. This is a typical way to actually apply this control net into a stable diffusion unit. This is stable diffusion unit, like you can see that encoder block and the middle block and the decoder block. This is the attention unit. Okay, here are a few of the example that this is in fact I trained in several times. It is difficult to train. It's quite difficult to train. And this is only a toy example. So in this example, we only generate some circles. I'm not exactly sure this is exactly the example toy example, but this one is very easy that we because I have several similar customization things. But this one, the benefit of this type of things is you don't need actually data. You can generate data by yourself because all we need is to get a circle and do a coloring. But you can see that comparing to like the pixel like in game, it is much difficult to train. Although it is pair, like we already have an input and output, it is it requires a lot of time to actually align, to get a desired output. So in this output, we also have some text prompt to tell the color of the circle and the background. So it does not exactly follow our text prompt instruction. In these examples, they are more or less, or at least what I can say is they are following the image condition. So this circle is more or less like this one. But the truth is, maybe at the first several epoch, you probably doesn't get this correct. The interesting phenomena of this type of training is that at certain point, it becomes magically, rapidly following the instruction. But you need to get passion because at the first several epochs, it is not going to be very encouraging because you will see that it almost does not following the text prompt closely and does not following the image conditionally also. But it will become much better at a certain point and getting better after that. So it also has certain suggestion in the paper. You can read the paper on how to find the breaking point and how to exploit that breaking point to do your training, to design your training。好，所以这边其实它不好训练，这个不好训练。那就算这么简单的例子，我这边的玩具例子，它其实都要花蛮久时间，可能接近，你可以想象比较像1天这种时间，或者1天到2天这种时间去训练。就算这么简单的一个例子，这个如果你用 pixel 的话，可能5到15分钟就训练完了，就会有还非常好的结果啊。但是这个东西不会可能也是因为它有 text prompt， 然后有各式各样，这个东西可能就要花到比较像1天的时间，然后它会有一个突然爆发的点，那个爆发点就有点像固定的，就一定要花这么多的时间去训练啊。所以他这边有一些建议让你品质，你可以看到原来 paper， 他会建议一些让它品质变好。但总之这个是不好训练的，虽然还蛮有趣的，但是这个我考虑拿来当作业，但是不好做，因为这个就算这么简单的，可能都要花到，就是你可能要花到1天。那万一你失败了，就前面那个 Dream Boost 你失败就你可以重新尝试，这个失败了要再花掉1天，这个会太过头。但是还是蛮建议大家。So although I didn't put it as a homework, but I strongly recommend that you try to at least for some toy example, or maybe after a toy example, if you have a certain idea, like okay, I want to do like a colorization. I have a black white photos. I want to do colorization, or maybe like super resolution or denoising, or maybe inpainting things. Then you can try it. It's if you have the resource to train and have some time, it is quite interesting experience. Okay, so what is the limitation of this type of training? As you can see that this we have a plus right addition right here. We edit the image condition with the image data. So because this addition, your your condition is limited to the structure or positional wise things. So you cannot do things like cat toy. Like, okay, we have a style of JoJo things. Please follow this style. Or please generate. We give you a certain example of object. We ask you to generate similar object. No, it is not suitable for this type of things. It is suitable for like post control or like coloring or like a super resolution. All this kind of application have roughly the same position align with the input image. That kind of like this one. You cannot just give like 2 images and they are okay, like one character and 2 characters. You want them to find a position of you ask the diffusion model to take these 2 characters and put them to do some like fighting or like taking a group picture together or something like that. You can only do that if they have aligned the position. This is because we do the addition right here. So there's nothing you can do or very difficult to do to separate the things because everything has already in the same position. You literally add them together. It is very difficult to separate. It is possible to separate the dimension like 1000 or 24 into very complicated interpretation. It is possible to do that, but it is very difficult. And because you add them, I mean, in every layer, it makes it almost impossible to do more like the face swap or things, similar things. Okay. So that's the limitation of this type of things. If you do a concat things, then maybe, like we said, if you don't do the addition, do a concat, then maybe. But concat is not good enough. If you concat on the channel, if you concat on the like X, Y or things, then you can do other type of things. So that's the limitation of a control net. It is very suitable to do like pulse control, like a depth control, or like edge map things. But it's not suitable to do like mimic style or mimic the object. Another thing similar to ControlNet is T2I adapter. I think it is by Tencent. And another very popular way to do more things is like IP adapter. They are mostly about different way to inject information, the image condition information inside the architecture, inside the model. The T2I adapter did things similar to ControlNet. So it has similar, mostly similar limitation. It requires something like align with the position. Okay, so I forgot to say something is that it has some limited ability to define the position alignment of things because we are actually working on a latent space. So if you are working on the pixel space, like you're working on 1000 by 24 or 1000 by 24 image pixels, then it is almost hopeless to do certain like modifications. But because we are working on a latent space, the position is not that precise. So that's why we can do things like, I mean, if you do the depth things, you can slightly modify the shape. I mean, this one is kind of like the position, right? And we can modify the shape of people a little bit. Maybe like a depth map or things. We don't need to have exactly spherical head because we are working on latent space. So because of the latency, we have certain freedom. But mostly, you still need to have exactly the same in general. In a global view, in a macro view, they have the same position. So that's a limitation. Okay, so let's go back to T2I adapter. It have a similar limitation. One of the specialty is that you can stack several different T2I adapter together to have multiple effect on it. This one is similar to LoRa. You can stack several LoRa together and stack several. In fact, you can do a similar thing like multiple control net. This is a similar thing. The paper emphasizes on this capability, but as you can see, that LoRa and control net all share the same property. The primary difference between T2 adapter and the control net is that the different way to inject the conditional information to the things. Okay, so this is T2I adapter. T2I adapter is a little bit easier to train. Because as you can see that in control net, you are training pretty much the similar parameter than the original weight. Maybe not that much, but you are pretty much get like half of the original network. So this one is still a very huge thing. Although you start with a trainable copy, but because you're using a lot of parameters, so that's why probably one of the reasons that it requires a lot of time to train. So one simple way to solve it is like LoRa. So you can see like control LoRa things. There is control LoRa control net. That's a very apparent, obvious way to variation, a very apparent variation of the original control net. But T2I adapter is easier to train. So, but it is still using addition to the layer, but it did it in a more straightforward way. So by given any kind of image condition right here, what it does is to actually train a totally new model that transform this image into some latent comparable to the unit input and output. So that's it. Suppose we have like 2 or 3 it doesn't matter. It's similar. So you can just fill the first one. So suppose we have this, like a HMAP sense. Then you train a model that convert these things into a latent that is compatible to the things right here, so that you can add them together. So precisely, so each one, the condition, you can see that we are into we first do a pixel unsharable things and the convolution and everything. Also, this is a convolution block and residual block things. And it has to do some certain kind of downsample. This is because the data space is a downsampling space. Anyway, it doesn't use VAE or anything. It train from scratch and get things. And for each layer you want to inject information, it has a different output. So it has certain network design to kind of sharing things or things. That is secondary. The whole idea is that it trained to have a multiple output. So each output is used to add directly to the layer right here as an input. So you kind of fixing everything of the original model, but you are trying to fit, and maybe there are some holes or like small subspace in the original latent space. You try to find a way to inject your information inside it. But all you need to do is to train a separate adapter or encoder to do the things. And this things is quite straightforward. And because this model can be pretty small, depends on your choice. So you can decide to make it a larger model to be more complex or simpler model. But everything is very straightforward and direct. We simply modify the input of each layer directly. That's it. So T2I adapter is another alternative, can be considered as an alternative to a control net. And it has a similar things to add something into the original and doesn't modify the original diffusion model unit. And it adds things into it. But it does it more like a straightforward and direct way to, okay, we don't care anything. We just try another model. And doesn't matter, it has many output because we need to modify a lot of different output. So we actually, what we did is pretty simple. We have multiple outputs to do the injection, and that's it. Another thing is more interesting is called the IP adapter. The IP adapter is more like okay. So another way to inject image condition is to pretty straightforward. Is to okay, we extend the attention space so that it can reference to our attention. Okay, because the denoising unit is actually attention unit. So, or maybe we're using a DIT. But anyway, there are some layer that do the attention. Attention is kind of like referencing to something. So, so first of all, IP adapter does not have the limitation of like control net and T2I adapter, so that you will have to align everything together. It is more like we can transfer a texture or style or maybe an object to the things. The basic idea is to use the attention space. So when we do the attention, we inject information so that like in a like in a key value. So when we do the query, you can query. It is possible you can query to this key value space. But how do we, in fact, do add this attention inside the original model? So one way to do that is that if we have certain attention layer, we simply expand the key value things at that layer, or maybe we can add one more attentional layer right there. Also, that is a naive idea to do that. So, but that idea works, but it has certain drawbacks to the quality things. So, IP idea adapter is actually non-trivial, and it has some certain concrete contribution of the architecture design. It is not just a logical thing. It addresses certain potential, or I mean certain drawback of the naive approach. So this is way that people actually use to one way people actually use to if the goal, I mean the idea is to try to increase the attention space and use this as a way to inject new information into like denoising unit or like transformer block. So how does it does? So first of all, it I mean for the text prompt it uses the same things to do cross attention. This one is the text encoder things. But for an image encoder, it actually train adapter right here. It is linear normalization, image features, and this one is trained separately. And it actually decouple the cross attention right here. So there is a cross attention for, I mean, in stable diffusion to do the things like so that the text encoder can be used. Like we said, we can inject image information inside. Is way to do that. But here it use a decoupled cross attention layer right here to train it right here. So it does not affect with the original cross attention for the text things. It is in fact fixed. It train a separate cross attention to the image. So it's still so you can see that the IP adapter with the key point is it has a decoupled cross attention. So this architecture works on this kind of setting. So the basic idea is simple. We kind of want to inject the information from the conditional image inside the attention. Because in the attention, it is not added to the latent. So it is not limited to the position. So you can swipe the face or use the style. It potentially you can do that. But how do you actually to make it to use this cross attention? So first of all, you need an adapter, a separate adapter to extract the image information. And also you need another cross attention layer to train it separately from, you don't mess up with the original text decoder. So everything is frozen. The text to image model, everything is frozen. But you add another cross attention layer specifically for the image. Okay, so this is how the IP adapter does. So if you are using Comfy UI or like other diffusion, like web interface or like A1111 web interface or other thing, you will see a lot of like IP adapter, LoRa and the control net. Maybe sometimes you'll see T2I adapter, but all of these things are certain ways or easy way to do the things. So in this one, you can do like impending. You can see that the face is not in the same position. They are not necessary to be at the same position. But also, if you wish to do things like control net, it is possible to do that. But without this limitation, you will need to give it enough information so that it understands what you actually means. Okay, so unfortunately, we are unable to cover like Stable Diffusion 3 or like advanced things. So we will do this next week to cover more modern techniques. Maybe we'll also include like the latent LCM, latent consistent modeling, um, and other things. Like so next week we are talking about advanced techniques in the Stable Diffusion. But I think the fine tuning is pretty interesting. So for not only for homework, it's also pretty fun to do your own, to customize your own image generator. So I'm encouraging you to actually try a bunch of different ideas. Maybe not limited to homework like a Dream Boost. You can try like IP adapter or like a T2I adapter. A control net is a little bit to take too much time, but if you have 1 or 2 days free of machine that you can use, feel free to try it. It is still very okay. No, the control net is difficult to track. So T2I adapter is kind of easier, but control net you probably will fail if you try your own idea. It will probably fail. It is possible. If you are just trying something very regular, very normal, then you will probably just take like 1 or 2 days after you get your result. But if you try something like more creative, it will have more risk to fail. So just warn you that if you want to try to train control net, maybe it is not that easy. But other than that, I mean, other models like texture inversion is pretty easy. Dream Boost is homework. You have to try it. It is not difficult. LoRa, if you have a certain style and try to do the LoRa training, you will not fail. You will not fail. T2I is easier than control net. It still requires something. It still you can still fail if you have certain idea that is too. But there's a notebook in the Hugging Face notebook, diffuser notebook. There's T2I adapter. Also it has something for video. My experience is it requires some time, but the successful rate is much higher. The waiting time is much lower than the control net. I haven't tried too many about IP adapter, but so I cannot say much about IP adapter. But the IP adapter, there also has a lot of notebook that you can try. I believe it should be easier than. It's not more difficult than control net. So feel free to try and have some fun. Okay, so that's all for today's lecture. So see you next week.